This is the first of two screencasts that I'm producing to describe a interactive web application using the Shiny platform, which is part of the R programming language, to develop teaching applications for a module that I've taught for the last couple of years called Earth and Life. The model is concerned with the long-term controls on global temperature and also investigates some of the processes that occur during Snowball Earth events and the role that planetary energy balance plays in the processes that control temperature through those events. The second screencast will run through some of the science and go through the answers that the students should find when they run through the exercise, but this first screencast is about the development and deployment of the interactive model using the Shiny platform. So Shiny is developed by RStudio, who make various tools for the R programming language or scripting language. This is some R code here. A Shiny app that's deployed on the web consists of 3 R files at a minimum. A file called server.r that describes the interactions between the numerical code underpinning whatever the web application is doing. UI.r, which is the user interface component, and this is in this case it's called whackprac.r because that's the name of the short name for the practical, and this in this case contains the science stuff. So the science is described as a series of functions that can be called in a nested fashion, and what the model does is effectively calculate temperature, global temperature, on the basis of a set of conditions and feedbacks, one of which is the carbonate silicate weathering feedback, which is one of the key, understanding of which is one of the key learning outcomes for this, the exercise that this model is used for. The inspiration for developing this tool came from a student who was on the module a few years ago called Josh Nightingale, who turned up to one of the numerical practicals with his laptop, coded all of the equations up, and used R to do the calculations that the other students were doing with pen, paper and calculator, and therefore managed to save himself quite a lot of time and develop a little tool that he could then use as a revision aid subsequently, which I thought was a great idea. So Josh and I worked on the first iteration of this. In total, the development of this interactive model probably took about 15 person hours, so not an insignificant amount of time, but worth it probably in terms of the usefulness of the output. So the model is deployed either within the RStudio environment, which runs its own web server, so you can run it on a machine not connected to the internet, or it can be uploaded to the cloud, where it can be hosted, for instance, at shinyapps.io, which will do free hosting, but only for a limited amount of sessions or amount of time per month. So it doesn't actually make it practical to do it this way through Shiny Apps for a large student practical, because you have lots of people using it at the same time. But there are other ways of deploying it, which I will describe shortly. But first, let's take a look at the model. We'll click on whackprac. So the reason it's called whackprac is that it utilizes the core of the model is a set of equations developed by Walker, Hayes and Casting in a seminal paper in 1981 looking at the carbonate silicate weathering feedback, hence the abbreviation. So if we go into the application, this is now running the model that was described in the code that I showed earlier, and as you can see we have a series of tabs that the students can work through there's a worksheet associated with it that provides a bit of guidance, so it's not designed to be used completely standalone, although a second version might well include some more documentation, so the associated sheet isn't needed. So the students face a series of questions on the first one, deriving a simple equation, which they do on pen and paper, and then they can hit plot and see what the relationship looks like. So this is a simplified representation of the increasing incoming solar radiation through time as the sun warms. So this practical is all about energy balance, the balance between the energy coming in and the energy coming out, which is obviously in some way related to planetary temperature. So this is reproduced from the original question sheet from the old numerical pen and paper practical that this exercise, this interactive workshop was based on. So again, they do some kind of thought experiment stuff here to derive the equations that are then used, but they're already coded in the model, so they don't need to do the calculations. So skipping forward to some slightly more complex parts of the model, you can see these first 5 tabs take the students through all of the components of the model, and so this panel helps the students to understand the carbonate silicate weathering feedback, and you can see there are a series of sliders and some plots, and what the sliders allow us to do is investigate the nature of this feedback. So if I just hit the plot button, that will plot a line which should then appear as we tune the albedo of the model. So the students first tune the albedo of the model so that they find the solution for the present day, which is when the green line and the pink line touch at a CO2 value of 1 times the present atmospheric level. So that's effectively the present day. So the pink line shows the relationship between the temperature of the Earth and the CO2 concentration, and that's controlled through the weathering rate. So as the temperature increases, the weathering rate increases, and atmospheric CO2 is drawn down. The green line shows the relationship between CO2 and temperature. So that sounds like the same thing, but actually it's the other way around. That's the greenhouse effect, so that's the effect of CO2 on temperature, rather than the pink line, which is the effect of temperature on CO2. Now, key thing for the students to understand is that these are two simultaneous equations, effectively, and so the point at which these two lines intersect is the stable, steady state of the system. So that's the solution. After the process underlying the interactions and feedbacks that are being described have evened out, that will be the resting point for CO2 and temperature. So what the students can then do is, using this slider here, effectively go back in time. So if we pull time back to 500 million years ago, 500 million years ago, you can see that S, the solar constant, has decreased. So the amount of energy coming in has decreased, which means the weathering rate has also decreased, which means we find a new equilibrium between temperature and CO2. And as we run the system back, if there was no interaction between weathering and carbon, temperature and weathering and carbon dioxide concentration, 1.8 billion years ago, the temperature, CO2 still at 1 times present atmospheric level, would be way below freezing. But thanks to the interactions between temperature and weathering, CO2 is probably much higher, possibly 50 times present atmospheric level. There's a great deal of uncertainty in these functions. It's conceptually and qualitatively that we want the students to understand this, rather than for them to well, in fact, it's important for them to recognize that the quantitative solution to this model isn't necessarily very well constrained. So that's one of the key concepts that the students need to grasp, or that we want the students to grasp when they're doing this practical, when they're doing this workshop. And it's something that most students, before we introduced this workshop, weren't really grasping through the lectures and the other way they were explained, or through doing numerical exercises on paper. But being able to effectively twiddle the knobs on a carbon cycle and climate model and look at the solutions, that we found that helps them to understand mechanistically the processes underlying this key feedback. So this is all brought together on page 6, on tab 6, that presents the whole model. So we can change time, we can change the albedo, which is the reflectivity of the Earth, we can add some methane in if we want, we can take the system away from steady state, which becomes important when we're looking at rapid changes, for instance, after the evolution of oxygenic photosynthesis and the production of oxygen and the rise of oxygen in the atmosphere. There's very sudden deviation from this carbonate silicate equilibrium due to methane being very rapidly removed from the atmosphere, which probably drove a big Snowball Earth event. To be able to solve that in the model, you need to be able to remove that long-term equilibrium control and look at the short-term control on temperature. They're able to choose whether they use the classic Walker Hazen casting CO2 greenhouse or a different one, so that just changes the function that's being used, and they can play with weathering rate changing through time, or volcanic outgassing of CO2 changing through time. So there's a series of instructions here to run through and questions for them to solve, and they can then use the model to do these experiments. This is really a very simple long-term climate model that the students are able to use in the workshop to understand the system better. So as I say, this took about 15 person hours to develop. It's imperfect. It's definitely a work in progress. It could be streamlined and smooth, and probably some of the questions and exercises could be improved as well, but it's a good proof of concept. So the development time was about 15 hours. However, the deployment time to stick it on the web was next to nothing. So I'll just show you how that works. I have an account at shinyapps.io, and from that I can get the information that I need to run a command in R that will upload the application to the cloud, and it will be accessible publicly. So if I go to tokens, I can get the key bit of code that shows that tells Shiny Apps what my account details are. If I copy those to the clipboard, I can then go to R, and I can run this command down here, and that now connects RStudio, the development environment, to my account on shinyapps.io. And so now we simply run the command deploy app. So we need to call the library RStudio Connect, and then run deploy app. And it packages up all of those R files within the application directory, all of the ones that are required, meets all of the dependencies there might be for R, and uploads the latest version to shinyapps.io. So that's deployment to the web. I don't think we'll be able to see anything through the web interface, because it will look no different to how it was before. So here is the application, if we go back to the list of applications, you see there's still one there, but now the deployed date has become today's date, whereas previously it was yesterday's date when I uploaded it for the first time. So this hasn't been uploaded before because, as I mentioned earlier, there's a limited capacity through the free hosting in terms of the number of simultaneous sessions and the number of user hours per month. So there is another alternative which works well in the IT teaching spaces at UEA, which is that RStudio has its own inbuilt web server. So if we go to either ui.r or server.r, which are the sort of core shiny R code files, we can hit the Run App button up here. Some unintended changes there, and that launches a browser within RStudio that allows us to run this model. Now, one problem that came up on some machines when we ran the practical with the students was that some of the symbols went a bit funny, so that should be Greek sigma, not a capital I with an umlaut on top. So a few teething problems with the software, but nonetheless it gets the story across for the students. So this can be deployed in any of the teaching spaces with ease. So it proves quite a useful teaching tool when we want to run models with the students. There are a few other models that are used within the Earth and Life module that were developed by Andy Watson a few years ago when he ran the module, which are quite effective. But there are a few problems, particularly as Microsoft software ceases to be backwards compatible. Every year we have to make some modifications to keep the models running. So hopefully this is a more future-proof way of taking a similar approach, but it's also a bit more interactive with a proper user interface. With Excel it's very hard to achieve things like slider bars and simple input-output type user interfaces. So I feel it's a powerful tool that hopefully will be used more for teaching in the future.